Hello there. This tutorial is brought to you by the Atılım University Open Courseware project. This is the third video section of the video lecture series of Physics 101. The lecture notes are prepared by Associate Professor Dr. Hüseyin Oymak, and the lecture is given by Ümit Alkuş. This tutorial is about vectors. Before I start, let's have a look at the topics we will cover here. First of all, we will define scalars and give some examples of them in physics. Next, we will talk about the definition of and notation used for vectors. In order to illustrate vectors, we introduce the displacement vector. Immediately after that, we are going to discuss the basic properties of vectors, which might be listed as the null vector, equal vectors, vector summation, scalar multiplication, subtraction of vectors. With these all properties in mind, we will examine how to resolve or decompose a vector lying on an xy plane. Specifically, we will introduce the unit vectors. Later, we will generalize our discussion to three dimension. That is, we investigate vectors in space. Subsequently, two extremely important 3D vectors will be examined, one of which is the position vector and the other is the displacement vector. In the last analysis, we will learn the scalar product of two vectors as well as the vector product of two vectors. Okay then, let's start our lecture. In physics, many physical quantities are described by a single number. If no additional information such as direction is needed, then this quantity is called a scalar quantity. In particular, volume, mass, energy, heat, temperature, electric current, so on and so forth, can be seen as scalar quantities. Now we are ready to discuss vectors. In physics and in all engineering sciences, we encounter with a large number of quantities that have not only direction but also magnitude. Recall from the video lecture 2, that is motion along a straight line, position, displacement, velocity, and acceleration are such quantities. As you see in this figure, we geometrically represent them by arrows, like this. And naturally, we denote them by P1, P2, and we put an arrow on the top of the letters, which reminds you of that the tail of this arrow is at the point P1 and the head of that is at the point P2. Well, in the next slide, we will learn how to denote a vector by a single letter. In handwriting, we put an arrow over a letter to denote a vector. In print, we use a single letter written in boldface type. For example, the vector in the previous slide is denoted by either this notation or this notation. Since vectors have both direction and magnitude, the magnitude of the vector A is the length of the arrow. N is denoted by a slanted letter in print and single letter in handwriting. In the lecture notes and also in these slides, we use the print notation to represent a vector. However, in your notes and also in the exams, you have to use the handwriting notation. Now, altogether, it is better to talk about the displacement vector. Now, remember the discussion in Chapter 2. If the initial position of an object is x1 and the final position is x2, then the change in the position, that is delta x, x2 minus x1, is called the displacement in one dimension. Similar discussion holds here. Suppose that an object moves from a point P1 to point P2. Then the vector whose tail is at point P1 and the head is at point P2 is called the displacement vector. It is important to note that the displacement vector does not tell us the actual path. In fact, the actual path might be this one, or this one, or even this one. In other words, displacement vector is independent of the path. As you will see in the next chapter, the magnitude of the displacement vector will be called distance, and also that of velocity, speed. Good. So far, we have seen how to represent a vector and displacement vector. In the following slides, we will learn the basic properties of vectors. The first property of vectors is that the vector with zero length and no specific direction is called the null vector or zero vector. In your calculations, please don't forget to put an arrow over 0. Then comes the second property. In this part, we define equal vectors. First, look at this figure. For the simple reason that both vectors A and B have the same magnitude and also direction, they are said to be equal vectors. They are equal regardless of the starting points, that is, tails. This is so since vectors are transportable, and any vector can be slided completely arbitrarily to another place, keeping the direction and magnitude the same. However, this discussion is not valid for the position vector, because its tail has to sit just at the origin. Therefore, two position vectors with same length and direction are equal if and only if their tails are at the same point. This is an extremely important exception, and you have to know it very well. Good. Making use of the property that vectors are transportable, it is time to move on to the new topic, vector summation. We have said that vectors have both magnitude and direction. Thus, summation and also subtraction operations cannot be treated as that of ordinary numbers. For example, consider two vectors a and b as in this figure. A and b can be summed geometrically by tail-to-head fission as follows. We place the tail of b at the head of a, and the tail of the vector sum is placed at the point where the tail of a is, and the head of the vector sum is placed at the point where the head of b is. The vector sum a plus b is called their resultant or net vector. Keep always in mind that it is impossible to apply a vector summation on the vectors of different kind. For instance, a velocity vector and a force vector cannot be summed because the result is both physically and geometrically nonsense. For the following discussions, please look at the figure 4 in the previous page. As an example, if A and B are two displacement vectors of an object moving from point P1 to point P2, their sum A plus B will give the overall or net displacement of the object. In the previous discussion, we said that the summation of the vectors is also a vector. And the mathematical formalism is that vector C equals vector A plus vector B. As we will cover in the next discussions, if A and B are three-dimensional vectors, then C is also a three-dimensional vector. And we state that the x component of C, say Cx, is equal to Ax plus Bx, and Cy equals Ay plus By, and also Cz equals Az plus Bz. Again, if you visit the figure 4, you can easily show that vector summation operation is commutative. In other words, the order of the summation is of no importance in terms of the resultant vector. If three or more vectors, say A, B, C, are involved in a vector summation, it is allowed to sum first A and B, and then sum the resultant vector A plus B and C. Okay, in the following slide, these four cases will be demonstrated geometrically. Now, let the three vectors in this summation be these vectors A, B, and C. In the first summation, as is shown in figure A and B are summed, and then B and C are summed. The tail of B is placed at the head of A, and the tail of C is placed at the head of B. The tail of the resultant vector is placed at the tail of A, and the head of A plus B plus C is placed at the head of C. In the second summation in figure B, first A and B are summed, and the resultant vector A plus B and C are summed. The tail of the resultant vector A plus B plus C is obtained by placing its tail at the tail of A plus B and its head at the head of C. In the third case, in figure C, first B and C are summed, and then A and B plus C are summed. The resultant vector A plus B plus C is formed by placing its tail at the tail of A and the head at the head of B plus C. In the last summation shown in figure D, we group A and C to obtain the sum A plus C, and later we sum B to A plus C. The resultant vector has tail at the tail of A plus C and head at the head of B. Briefly, the resultant vector is the same for all cases. Well, this demonstration brings us to an end in the discussion of vector summation. And now, let's see another property of vectors, scalar multiplication. By definition, if a vector A is multiplied by a scalar C, the result is another vector C times A. The magnitude of this vector is the absolute value of C times the magnitude of A. If C is positive, say 2, 2/3, and 1/3, then C times A is parallel to A, as shown in this figure. If C is negative, say -1, -2, -2/3, -1/3, then C times A is antiparallel to A, as shown in this figure. For both cases, we can interpret the scalar multiplication as contraction or elongation of a vector. Multiplying a vector by C equals 0, the result is the null vector, that is, 0 vector. Multiplication by unity, C equals 1, leaves the vector unchanged. Multiplication by C equals -1 leads to the additive inverse of vector A, denoted by -A. It is obvious that The scalar multiplication is distributive over summation. That is, c times a plus b, or a plus b times c, equals c times a plus c times b. Combining the property of vector summation and also scalar multiplication, we can subtract a vector b from another vector a as a minus b, that is a plus minus b, where minus b is the inverse vector of b. Then we say that the vector subtraction a minus b can be seen as the vector summation of a and the inverse vector minus b. In the following slide, we show how subtraction is done geometrically. Now we consider two vectors a and b as shown in this figure. Then the additive inverse of a is nothing but the vector minus a, which is antiparallel to a. And the inverse of b is again the vector minus b, which is antiparallel to b. We can geometrically obtain the vector sum a plus minus b to obtain a minus b, and also b plus minus a to get b minus a by the tail to head fashion. However, there is an alternative way to remember the subtraction a minus b. We place two vectors a and b, not minus b, tail to tail, as in this case. The desired difference or subtraction a minus b is vector from the vector b, that is the second vector, to vector a, and in this case b minus a is the vector from the vector a to vector b. Well, we have covered all the basic properties of vectors, and this is a good point to start to analyze vectors in a more sophisticated manner. If we resolve or decompose a vector into its components, we find its projections on the axis of a coordinate system, which are found by drawing a perpendicular line from the head of the vector to the axis. Consider a vector A lying on an xy plane, as in this figure. Its projection on the x-axis is referred to as its x component, that is ax, and that on the y-axis as its y component. Since a vector is transportable, we can slide the component ay of a to the right to obtain the right triangle in this figure. Remembering the discussions in the vector sum, this figure shows that vector A equals the vector sum of components AX plus AY. If this vector A makes angle theta from the positive x-axis, then the magnitudes of the components of A are calculated to be AX equals A times cosine theta and AY equals A times sin theta. The relation between the three magnitudes A, AX, and AY in this right triangle is found by the Pythagorean theorem as A equals square root of AX square plus AY square, and tangent theta is nothing but the rate of AY to AX, and the angle theta is the inverse tangent of the ratio of AY over AX. It might be useful to notice that a vector A in an xy plane can be completely specified if we know first its components AX and AY, or its magnitude A and the angle theta it makes with positive x-axis. Pairs AX, AY and A, theta both convey the same information about vector A. We refer this notation as the component notation and this notation as the magnitude angle notation. Summation of vectors can be carried out pictorially in a simpler and more comprehensible way, as is done in this figure. Suppose we are after the result of the summation R equals A plus B. Recall the discussion of equal vectors. Then, as is clearly seen from this figure, the x and y components of the resultant vector are Rx equals Ax plus Bx and Ry equals Ay plus By, and its magnitude is found by the Pythagorean theorem as R equals square root of Rx square plus Ry square. And finally, the angle that R makes with the positive x-axis is found from tangent theta is Ry divided by Rx, or theta is the inverse tangent of Ry over Rx. So, this is the end of the discussion of resolving a vector lying on an xy plane. And the next thing we will discuss is the concept of unit vector. The unit vector A hat of the another vector A is defined to have a length exactly 1 and to be in the same direction as A. We form A hat by dividing A by its length A. That is, A hat equals the vector A over its magnitude A. If we rewrite this equation as the vector A equals the magnitude A times the unit vector A hat, then the most important equation about vectors is formed. In other words, we say that a vector is the product of its magnitude and its direction. A unit vector does nothing but specifies a direction. As you may easily notice, a unit vector does not have a dimension nor a unit. Consider the usual right-handed rectangular XYZ coordinate system. To check whether this coordinate system is right-handed, we write the names of the axes in sequence like X, Y, Z, X, Y, Z. Then we pick any three of them in this order. Say ZXY or YZX. Now, if we sweep the Z-axis with our right hand towards the X-axis, the upright thumb should point in the same direction as the Z. And this is indeed the case, so that we have a right-handed coordinate system. In this usual right-handed rectangular XYZ coordinate system, we shall use three special Cartesian unit vectors. I points the positive direction of the x-axis, J points the positive direction of the y-axis, and K points the positive direction of the z-axis. In handwriting, these unit vectors appear as I hat, J hat, and K hat. More specifically, the vector I hat is from origin to the point 1, 0, 0. J hat is from origin to the point 0, 1, 0. And K hat is from origin to the point 0, 0, 1. Then we write any vector A as a linear combination of these basis vectors as A is AX I hat plus AY J hat plus AZ K hat. This form is called the unit vector notation. Consider a two-dimensional vector A lying on an xy plane, as in this figure. Then the previous 3D vector relation reduces to A equals AX I plus AY J. Remember that AX equals A times cosine theta and AY equals A times sine theta. Then we obtain A equals A times cosine theta I plus A times sine theta J. Or, taken into the parenthesis of A, we obtain A times cosine theta I plus sine theta J. From the previous discussions, recall that ax equals a cosine theta and ay equals a times sine theta. Then we use the relation a equals a times a hat. Then the following relations are obtained. A equals a times a hat. Then a hat becomes cosine theta I plus sine theta j. Remember the figure 8 where we had considered pictorially the vector sum in an xy plane, that is r equals a plus b in terms of the components of the individual vectors. Now we perform this addition with the help of unit vector notation. Therefore, we have Rx equals Ax plus Bx and Ry equals Ay plus By. In other words, R equals Rx I hat plus Ry j hat, or Ix plus Bx times I plus Iy plus By times j. Combining all the results we obtained so far, the magnitude of the resultant vector r is obtained as r equals square root of rx square plus ry square, or in terms of the components of a and b, it is square root of ax plus bx squared plus ay plus by square, and the angle theta that r makes with the positive x-axis is found to be tangent theta equals ry over rx, or in terms of the components of a and b, it is ay plus by divided by ax plus bx. Or, as we previously discussed, theta is obtained as the inverse tangent of the ratio ry over rx, or in terms of the components of the a and b, it is the inverse tangent of ay plus by divided by ax plus bx. Okay, that's enough for discussion of unit vectors, and let's have a look at the vectors in space, that is, three-dimensional generalization of vectors. So far, we have given the essential properties of vectors, mainly in terms of plane vectors lying on an xy plane. In these slides, we shall generalize our preceding results to three-dimensional space vectors with the help of Cartesian unit vectors I, j, and k. For the sake of completeness, we begin by repeating the relation giving a vector A as a linear combination of these unit vectors, that is, A equals ax I plus ay j plus az k. Then, using Pythagorean theorem twice, we obtain the magnitude or the length of A as A equals square root of ax square plus ay square plus az square. It is not difficult to construct the null vector or zero vector in 3 dimension. We take all the components in the x, y, and z axis as 0. That is, 0 vector equals 0 I plus 0 j plus 0 k. We continue our discussion with the summation and subtraction of two vectors in 3 dimension. For example, if we have two vectors, say A with components ax, ay, and az, and vector B with the components bx, by, and bz, then summation and subtraction of these two vectors obtained to be r equals a plus minus b equals ax plus minus bx I plus ay plus minus by j plus az plus minus bz k. Or in terms of the components of r, we write easily that rx I plus ry j plus rz k, where plus sign here shows the summation and minus sign shows the subtraction. Then the magnitude of the resultant vector r is obtained to be r equals square root of rx square plus ry square plus rz square. Or in terms of the components of a and b, we write that square root of ax plus minus bx squared plus ay plus minus by squared plus az plus minus bz squared. Now we can discuss scalar multiplication of a 3D vector. For a given vector a and a scalar c, which is a real number, we now define scalar multiplication as c times a equals c times ax I plus c times ay j plus c times ax k, and the magnitude of c times a, that is absolute value of the vector c times a, equals the absolute value of the scalar c times the magnitude of the vector a. In addition, since scalar multiplication is distributive over the vector summation, we write that c times a plus b, or equally a plus b times c, the vector a multiplied by c plus the vector b multiplied by c. Now we are ready to discuss an example of a three-dimensional vector, that is position vector. Although we do not normally associate a vector with a definite position, There is a particular example called the position vector, whose tail is at the origin and whose head is at the point P of x, y, z, as in this figure. The position vector is commonly represented by R, as R equals xi plus yi plus zk. The position vector R is in general used to denote the position of a moving object at any time, as we will see in the next chapter. Next, we discuss the difference between two position vector, that is, displacement vector. Consider an object that starts to move from point P1 and arrives at point P2 as shown in this figure. The so-called displacement vector, denoted by delta R, which we have mentioned in the beginning of this chapter, gives the net change in the position of the object. It follows from this figure that delta R is nothing but the subtraction of two vectors, that is, R2 minus R1. Therefore, making use of the notion of vector subtraction, we express delta R as delta R equals vector R2 minus vector R1, or in terms of the components of R1 and R2, that is, x2 minus x1 I plus y2 minus y1 j plus z2 minus z1 k. Sometimes it is much more meaningful to learn the displacement vector delta R as the sum of R1 plus the displacement vector delta R equals R2. This relation has the plain interpretation that if an object initially at position R1 undergoes a displacement delta R, it arrives at position R2. Very good. Until now, we have discussed basic properties of vectors and investigated three-dimensional vectors such as position vector and displacement vectors. From now on, we discuss two special properties of vectors, that is, scalar product of two vectors and also vector product of two vectors.